Good morning, dear students. Welcome to another session of digital switching system. In previous class, we had discussed regarding two-stage network and a problem related to that. Let us continue further. So now we'll be discussing a three-stage network and its relevance, its design parameters, and we'll be solving a problem related to it. Now here we can observe. Here we can observe that we have three stages. That is, this is the first stage, second stage, and the third stage. So the first stage is the primary, next one is the secondary, and third one is the tertiary stages. And switches which are used in this respective stages are termed as primary switches, secondary switches, and tertiary switches respectively. Now in this case you can just see that there is something specified as A link and B link. So these are nothing but the connections which are present between the primary switch and the secondary switch, and B links are nothing but the connections which are present between the secondary and the tertiary switches. And now we have to decide on what should be the inlet, what should be the outlet, how many number of primary switches will be there, how many number of secondary switches will be there, how many number of tertiary switches will be there, and so on. Now if we consider the initial condition, that is if I have equal number of incoming and outgoing trunks, that is M is equal to N. So then what will be the overall design? So it is a simple case what we are considering, that is M is equal to N. So if that is the case, and if I assume that number of inlets for the primary switch is N, that is each of the primary switches having N number of inlets, then how many primary switches are required? So if I just look at that, I have N number of incoming trunks which have to be distributed as N inlets to each of the primary switches. Therefore I would require about N by N number of primary switches which is identified by G1. Now similarly, if I go to the number of tertiary switches which are required, here also we have N is the number of outlets which are present of the tertiary switch, and if these N have to cater to the N outgoing trunks, then how many switches are required? That is in the tertiary stage. So it is given, again this is given by number of outgoing trunks divided by number of inlets per tertiary switch, so which turns out to be N by N, which is denoted by G3. Now since there are N by N tertiary switches and N by N primary switches, now what indication is there should be a link for a link going from each of the primary switch to each of the secondary switch. So if this is one of the primary switches, there should be a link present between this and the first switch of the secondary, a link between this and the second switch of the tertiary, this and the third switch of the secondary, so on up to N by Nth link between the primary switch of this one and the secondary switch at this point. So therefore what it indicates is, it indicates that each of the switches will be having N by N number of inlets, because why is this specified is, apart from this switch will be receiving another inlet from the second primary switch, another inlet from the third primary switch, so on up to N by N number of N by Nth primary switch also will be giving an inlet to the secondary switch, so which indicates that there are N by N number of inlets. Now how is this outlets specified? Since there are N by N number of switches present in the tertiary stage, there should be a link going to each of the tertiary stage from the secondary switch. So first link to the first switch, second link to the second switch of tertiary, third link to the third switch of the tertiary, so on up to N by Nth link to the N by Nth switch of the tertiary. Therefore you have N by N number of outlets. Now here if we just observe, I have to decide on number of secondary switches, so which will be basically identified based on some parameter, that is how many number of outlets are present in the primary stage, and also it is identified by how many number of inlets are present to the tertiary stage. So that gives you the number of secondary switches which are required. So this is all the design parameter what we have, that is for m is equal to n, that is number of incoming trunks is equal to number of outgoing trunks. Number of primary switches, which is identified by G1, is equal to number of tertiary switches. So as we had seen in the previous diagram, it is n by n, because m is equal to n. Then n by n is a secondary switches inlets and outlets, that is n by n. What this indicates is, here I'll be having n by n number of here I'll be having n by n number of outlets and inlets, and at the other case we'll be having the inlets. Now regarding A links between the primary and the secondary, and B links are the links which are present between the secondary and the tertiary, that is what we had discussed. Now as an optimum design, if we consider the number of A links is equal to number of B links, then what is the overall design? If that is the case, then how many number of secondary switches are required? Now this is given by this parameter, that is number of trunks divided by the number of primary switches or number of secondary switches, so which will give me a value which is equal to lowercase n. Now I have to decide on number of cross points per primary switch, which is equal to number of inlets to each of the primary switch into number of secondary switches, which will give me as the result as n square. Now number of cross points in the primary stage is obtained by multiplying the number of cross points per primary stage into number of primary switches. So that is that will end up with this result, that is n into n. So in this case we can just observe n by n is the number of primary switches, and this one is the number of cross points per primary switch. On the similar basis, now we have a number of cross points in the secondary stage, which is given by G2 into this parameter. What it identifies is, this is the number of secondary switches, this is the number of inlets which are present. So on the similar basis, if we just identify number of cross points per secondary stage is number of outlets per secondary stage into number of tertiary stages, or we have to take the other condition, that is we can even identify using the tertiary stage. So if that is the case, so this is the end result what we get, that is n square by n. Therefore total number of cross points in the number of cross points in the tertiary stage is given by n into this parameter, which is n into n. So this is again identified based on the previous discussion what we had. So first we identify number of cross points per switch, and then using that we identify number of cross points in that stage. So in if I'm identifying for the secondary this thing, number of cross points in the secondary switch is equal to number of inlets to the secondary switch into number of tertiary switches which are present. Then if I am identifying for the tertiary switches, number of cross points per tertiary switch is given by number of outlets. Since it is the last stage, we have to consider this as outlets, number of outlets number of outlets for each of the tertiary switch into number of secondary switches, because before that we have just the secondary switch. So based on this we will be getting the number of cross points per switch in each of the stages. And if I want to identify the number of cross points in secondary and tertiary, so number of cross points in secondary stage will be equal to number of secondary switches into number of cross points which we have identified for the cross points per secondary switch. Similarly for tertiary also we obtain the same way. So that is what we have obtained in this two cases. So therefore total number of cross points is the summation of all the three cross points for all the three stages, so which ends up in this equation, that is capital N into 2n plus capital N divided by n. Now for obtaining minimum number of cross points, we have to differentiate C3 with respect to n and equate it to 0 as we had done for second stage. So, since this is 3, this identifies that this is a 3-stage network. So when we do that, we end up with this result, that is when we differentiate C3 with respect to n and equate it to 0, we obtain n is equal to square root of n by 2. So this is this gives us the optimum solution. Now when we substitute it in to identify the number of cross points, then it turns out to be equal to 2 into square root of 2 into n raised to 3 by 2. So this is the number of cross points for the optimum solution. Now next we have to check out for the other condition, that is say m greater than n or m less than n. Let us consider m greater than n, that is number of incoming trunks greater than number of outgoing trunks. So in that case, if you just consider let m be the number of inlets for each of the primary switch, n be the number of outlets for each of the secondary switch. Sorry, it should be a tertiary switch. It's a typo error. It should be tertiary switch. Therefore, if you just identify number of primary switches is equal to capital M by M, and number of tertiary switches turns out to be sorry, replace this also. It is number of tertiary switches. Number of tertiary switches is also equal to number of outgoing trunks divided by the number of outlets for that tertiary switch. Now if we consider G2 as the number of secondary switches, since I have to decide it based on the design values, so this will be identifying based on a problem. So let G2 be the number of secondary switches. Then I want to identify how many cross points are there for each of the switches. So this is a common the thing what we can use even when m is equal to n. So if we consider here, number of cross points per primary switch is equal to number of inlets to that primary switch into number of secondary switches, because I should have a connection from each of the primary switch to each of the secondary switch. So if I consider that, I'll be getting number of cross points per primary switch, which turns out to be m into G2. G2 is the number of secondary switches and m is the number of inlets for each of the primary switch. Similarly, we have number of cross points for each of the secondary switch as number of inlets for the secondary switch into number of tertiary switches. So which turns out to be m by m into n by n. Now number of cross points for the tertiary switch is, since it is the last stage, we have to consider the outlet. Number of outlets are for each of the tertiary switch into number of the secondary switches, because that is the switch stage which is present before that. So which turns out to be n into G2. Therefore, total number of cross points will be given by number of primary switches into number of cross points per primary switch, number of secondary switches into number of cross points per secondary switch, number of tertiary switches into number of cross points per tertiary switches. So which ends up in this equation. Now as we are discussing for m greater than n, that is for a concentrator, it identifies that the number of links, whether it is A or B, will be limited by the lower value, that is in this case it is the outgoing trunks. Therefore, in order to obtain an optimum solution, we can equate these number of links equal to n. So when we equate it to number of n, then overall what will be the result, that is what we have to check out in the overall design. Now in this case, the number of outgoing trunks capital N is given by number of primary switches into number of secondary switches, which is nothing but related to the outgoing trunks. Then number of secondary switches into number of tertiary switches, that is two immediate stages. It's a product of two immediate stages, number of switches present at each of the stages. Now if we just replace each of the parameters, we end up n is equal to number of primary switches into number of secondary switches, then number of tertiary switches into number of secondary switches. So when I make use of this equation and this, that is when I equate this parameter, I'll get G2 is equal to n. That is, if G2 is equal to number of outlets, if it is equal to number of outlets, then I'll be having a optimum solution. Because of this, if I substitute it in this parameter, that is G2 is substituted here, then what happens is I get the number of inlets at each of the primary stage should be equal to lowercase n into m divided by capital N. So this is what is happening, and when we consider the design parameters and if we substitute the above values in C3, we end up having this overall result, that is C3 is equal to m plus n into n plus n square by n. Now for minimum number of cross points, again we differentiate C3 with respect to n and equate it to 0. When we do this, this is the end result what we get, that is m is equal to m divided by square root of m plus n, and n turns out to be n divided by square root of m plus n. So these are the two design parameters what we will be considering for optimum solution. So if I have a number of inlets equivalent to this equation and number of outlets equivalent to these equations, then I'll be obtaining a design which will give me a optimum number of cross points, that is the optimum design. Therefore C3 will be when we substitute this is the final equation of C3 which will show me the number of optimum number of cross points. So these are the minimum number of cross points which are possible for the given design. Now let us consider a problem related to three-stage network. So when I consider a three-stage network, so here design a three-stage network for connecting 100 incoming and 100 outgoing. So you can see that if I represent it as m and if I represent this as n, the condition is it is m is equal to 100, m is equal to n is equal to 100. This is the case. So if this is the case, then how do I go ahead? Now first I should identify how many inlets are there and how many outlets are there. So for the optimum solution, we had obtained an equation, that is number of outlets is equal to square root of n divided by 2. So here since m is equal to n is equal to 100, when we estimate, it turns out to be 7.07. So when it is 7.07, now I cannot have number of inlets which is a decimal value as such as 7.07. I should have n as an integer value which is close to the value what you have obtained, that is 7.07, and it should be a factor of 100, that is factor of n what you are considering. So if I just see here the close values to 7.07 and factors of 100 are 5 and 10. So these are the two values which are possible. So now I have two design options for these things. So when I consider n is equal to 5, what happens? When I consider n is equal to 10, what happens? So that is what we have to discuss now. And when we substitute this in the cross points, so we end up having 3000 cross points. So this is the design what we have specified. So let us enhance this diagram. So here we can see that we have a solution for the two designs. So if I consider n is equal to 5, so what are the different what are the number of switches which are required and what is the switch size? So these are two parameters what I have to decide. So how do I decide on these things? Now as I know that m is equal to n is equal to 100, and when I estimate, I got these values, and the factors which are close to these values and are factors of 100 are 5 and 10. So if I consider n is equal to 5 and if I proceed, so here I am just giving what type of switch is present, that is primary, secondary and tertiary. Now if I want to decide on how many number of switches, so number of switches in the primary stage is given by capital N divided by N, which is 100 divided by 5, which turns out to be 20. Now I have to decide so this is one parameter which is known, and another parameter which can be identified is how many number of tertiary switches are present. So this is given by capital N divided by N, which is equal to 100 by 5, which is equal to 20. So I have 20 primary switches and 20 tertiary switches. Now here I have to decide on how many inlets are there and how many outlets are there. Number of inlets is given by this value itself. So number of inlets to the primary stage is obtained from N is equal to 5. So this is already identified. Similarly, number of outlets for the tertiary stage is also decided by that value. So these are the known parameters. Now from these parameters I have to estimate the other things, then I have to see what is the overall design. Now when I consider this case, so I have got to know that the number of inlets for the primary switch is 5 and I have 20 primary switches. Now what we do is we generally make use of the standard switch size. That is, if I have a switch of 4 by 4, 5 by 5, 10 by 10, so such kind of switch sizes are specified as standard switch sizes. And if I have switch sizes such as 4 by 5 or 5 by 4 or any non-equal numbers, then it turns out to be a non-standard form. So wherever possible we try to make use of standard switch size. So here let us consider that this switch size is 5 by 5 because there are 5 inlets. Let me assume that there are 5 outlets, so 5 by 5. So what does this 5 indicate? 5 outlets implies that there is one link going to each of the secondary stage. So what does this indicate is, this indicates that there are 5 number of secondary switches. Now once we have obtained these 5 number of secondary switches, now this again gives us an indirect indication that there should be a link present between the secondary and the tertiary. From each of the switch, one link should go to each of the switch of the secondary. So what does this indicate is, since there are 5 switches, you will be getting 5 incoming or inlets for each of the tertiary switch. So therefore what it indicates, number of inlets for the tertiary switch is equal to 5. Because there are 5 secondary switches, I will be getting 5 connections from each of the secondary switch to each of the primary switch, tertiary switch. Therefore this turns out to be 5. And because this is 5 and this is also known, that is it is 5, it gives us an indication that the switch size is 5 by 5. Now another parameter is to decide what is the switch size of the secondary. We identified how many primary switches are there, how many number of inlets, what is the size. So because of this, the number of outlets is equivalent to 5. Because of this, the number of secondary switches is also 5, and this also gives an indication that number of inlets to the tertiary switches 5. So we obtained all these parameters. The only parameter remaining is this case, that is how many number of outlets should be present for the secondary switches. So if we just observe with respect to number of outlets, as we discussed that there should be one link which should be connecting to each of the tertiary switch from each of the primary switch. Now since there are 20 tertiary switch, there should be 20 outgoing links from each of the secondary switch. Therefore there should be 20 outlets for the secondary switch, which gives us a size of 20 by 20 for the secondary switch. So this is the design when we consider N is equal to 5. Now what if we have N is equal to 10? So when we have N is equal to 10, we can observe that we have again 3 stages: primary, secondary and tertiary. Number of primary switches is given by capital N by N, which is 100 by 10, which is 10 number of primary switches. Similarly, tertiary switches is N by N, which is 100 by 10, that is there are 10 number of tertiary switches. Now this is another parameter. Since N is equal to 10, it gives number of inlets is equal to 10 and number of outlets for the tertiary switches is equal to 10. Now so this is nothing but the parameter which is specified here, and this N is equal to 10 is nothing but the parameter which is specified here. Now as discussed, let us assume that this primary switch size is a standard size, that is, since there are 10 inlets, let us assume that there are 10 outlets. So if we consider 10 by 10 as the outlet, so then the 10 number of inlets is specified here, switch size is 10 by 10. Now what does this 10 indicate? It indicates that there are 10 outlets. It indicates that there are 10 links which are going to the secondary switches. So each of the primary has 10 outlets, and these 10 outlets are reaching each of the secondary switch. So it indicates that there are 10 number of secondary switches. Now since there are 10 number of secondary switches, it also indicates that from each of the secondary switch, one link will go to the each of the tertiary switch. So this indicates that the number of inlets to the tertiary switch is equal to 10. Now since I got to know that number of inlets for the tertiary switch is 10, the size of tertiary switch turns out to be 10 by 10. Now how many number of outlets are present for the secondary switch? So this is identified by how many number of tertiary switches are present for this case. So in this case I am having 10 number of tertiary switches, so which indicates that there should be 10 number of outlets for each of the primary switch. So therefore each of the primary switch will be having a size of 10 by 10. So this is the design for the second case. So this is the grading diagram, or the switch diagram what we have. So we have n number of, if I consider from this instead of table, if I go for design in this form, we can observe that if I consider n is equal to 5, that is each of the primary switch is having 5 inlets. So that therefore in order to cater to 100 incoming trunks, how many switches should be present? So it is 100 divided by 5, which turns out to be 20 primary switches. Now since there are 20 primary switches sorry 20 primary switches, it indicates that in the secondary switches, one link from the first primary switch, second link from the second primary switch, third link from the third primary switch, so on up to the 20th primary switch. A 20th link will go from the 20th primary switch. So which indicates that there are 20 incoming inlets to the primary to the secondary switch in the secondary stage. Now I should decide on how many switches are present. So this is decided by how many outlets are present for this case. So if I just observe, since I use a standard switch size, say because inlets are 5, let us assume that we have 5 by 5 switch size. Then since 5 outlets are there, one inlet to the first switch of the secondary, next inlet to the second switch, next inlet to the third switch, so on up to the fifth inlet to the fifth switch. So what does this indicate? That there are 5 switches in the secondary stage. On the similar basis, we have to estimate how many number of switches are there in the secondary switches and how many number of inlets are provided, because n is equal to 5. So if we just observe, this is the overall solution what we have for the first case. In the similar basis, we can have the design solution for the second case. So this is the switching diagram for the second case. So on the similar basis. So let us stop the session for today. Thank you.